Struggling to book a flight? Juggling endless dates, prices, and layovers? Imagine an AI that handles all the scrolling, clicking, and decision-making for you, effortlessly. Let's meet UITARS, the pure vision-based native GUI agent from ByteDance. Unlike traditional models that rely on textual inputs or modular frameworks, UITARS operates solely on screenshots, mimicking human-like reasoning to perform complex tasks. It outperforms GPT-4o and Claude Computer-Use on over 10 benchmarks, and it's completely open source. Stick around as we dive into it. Let's go!
UITARS is an innovative GUI agent model designed to interact with graphical user interfaces using only screenshots as input. Unlike conventional frameworks like GPT-4o that rely on complex, handcrafted prompts and workflows, UITARS simplifies this process through an end-to-end design. This model can perform human-like interactions such as keyboard and mouse operations and achieves remarkable results across benchmarks. For example, in the OS World test, UITARS 72B scored 24.6 with 50 steps, outperforming Claude's 22.0. Similarly, in Android World, it scored 46.6, leaving GPT-4o's 34.5 far behind. These achievements stem from four key innovations. First, its enhanced perception leverages a massive dataset of GUI screenshots, enabling it to understand UI elements contextually and with precision. Second, its unified action modeling streamlines actions across platforms, allowing for consistent and accurate interactions. Third, the incorporation of System 2 reasoning enables deliberate, multi-step decision-making by simulating human-like processes like task decomposition and reflection. Lastly, iterative training with reflective online traces helps UITARS learn from mistakes and adapt quickly. The bottom graph highlights these advancements, showing that UITARS significantly outperforms competitors in benchmarks such as Visual WebBench, ScreenSpot, and Android Control. The accompanying table breaks down these improvements, revealing gains like a 33.53% boost on OS World tasks and up to 42.9% on GUI Odyssey. This combination of detailed analysis and exceptional results solidifies UITARS as a leader in GUI automation. GUI agents are all about making digital elements like buttons or text boxes easier to handle. But there are significant hurdles. Older methods rely on text-based representations like HTML or accessibility trees to understand interfaces, but these can be inconsistent and not very adaptable. A common workaround is the modular framework. One part interprets the screen, another manages memory, and so on. But that can be clunky and brittle. That's where native GUI agent models come in. Instead of relying on text-based representations, they process full screenshots, much like we do when we look at a screen. They also move away from modular designs, going for an end-to-end approach that can flexibly handle new layouts. Of course, GUIs are complex. Agents need to parse dense visuals, plan actions, keep track of past steps, and precisely execute commands like clicks or text entries. Selecting the right data to train them isn't trivial either, since it requires detailed examples of human workflows. This paper walks us through how GUI agents evolved from rigid, rule-based systems to these advanced, adaptive models, teeing up the improvements in automation we see today. Here's a real-world example. UITARS, helping someone find flights from Seattle to New York. It starts by typing SEA into the origin field, then clicking a drop-down suggestion. Next, it picks a date from a calendar for departure, and then does the same for the return date. It even applies filters to sort results by price, clicking on the right buttons and rerunning the search. As the user scrolls through flight options, the interface updates in real time. What's fascinating is how UITARS handles issues along the way, like slow network responses or the user picking the wrong date. It suggests retry steps or corrections, showing that trial and error learning is key to dealing with real-world uncertainties. Look at the figure shown here. You'll see orange highlights for its thought process, blue markers for completed steps, and green notes for reflection. These elements make the system's reasoning transparent, illustrating how perception, reasoning, and action all come together. Now let's dig into the main features of UITARS. First is enhanced perception. It learns from a huge set of GUI screenshots, extracting key details like element types, spatial layouts, and subtle changes on the screen. This lays the foundation for advanced tasks, things like describing interface components in structured text, or answering questions about how the GUI looks. Next, there's unified action modeling. Basically, UITARS maps out the most common user actions, clicks, scrolls, typing, into a single framework that can be applied across different platforms. That means more consistent behavior, whether it's on a phone or a desktop. Then comes System 2 reasoning, which is that deeper, reflective thought process. It does things like decomposing complicated tasks and reflecting on possible errors, especially useful for multi-step workflows. And to keep improving, UITARS uses iterative refinement. It collects interaction traces from various virtual machines, filters them, and continuously updates its knowledge. Reflection tuning is part of that process, so it can spot its own mistakes and learn effective recovery steps. The result is a system that's more accurate and requires less human oversight. Here we switch gears to overall performance. UITARS stands out against competitors like GPT-4o in more than 10 benchmarks. Let's break it down. Perception. It handles complex screen layouts better than most. For instance, UITARS 72B scored 82.8 on a web interface challenge, beating GPT-4o by a wide margin. Grounding. It links GUI elements to their precise locations, achieving top marks in tasks such as ScreenSpot Pro. Agent capabilities. Benchmarks like OS World and Android World show UITARS acing complex tasks with fewer errors than other models. Then there's a quick tour through the evolution of GUI agents. Early rule-based systems, like what you see in robotic process automation, were good at copying repeated user actions, but would fail the moment something changed. They also relied heavily on direct system access, limiting flexibility. Eventually, teams started developing GUI-based agents that interact visually with the interface, not just via rigid, scripted rules. This shift opened doors to more adaptive, learning-based systems. Continuing the evolution story. Agent frameworks take these concepts further. Armed with large models such as GPT-4, they introduced multi-step reasoning and the ability to adapt to different tasks. Instead of using a big list of if-then rules, these frameworks rely on foundation models that interpret the environment and respond dynamically. So-called Stage 2 inches agent frameworks like AutoGPT and Longxiang go even further. They integrate outside tools and services, adding specialized modules for memory, planning, or task execution. Systems like Cradle store past experiences to improve over time, and an agent workflow memory (AWM) module can recall relevant workflows. Reflection-based reasoning also gained ground frameworks like React refine decisions based on feedback, while others, e.g., Navigator and CACT, handle multimodal tasks or replicate browsing behaviors. It's a major jump in flexibility and intelligence, laying the groundwork for more native approaches like UITARS. But there are downsides to traditional frameworks. They need a lot of manual work to define workflows and prompts. Whenever an interface or task changes, developers have to rewrite big chunks of code. Plus, each module learns separately, so knowledge isn't easily shared throughout the system. That leads to issues like fragmentation and frequent debugging. Enter native agent models. These embed all that workflow knowledge right into the model, bypassing the need for complex modules. The entire system, perception, reasoning, memory, actions, becomes an end-to-end learner. That offers huge benefits. Holistic learning. The model can adapt to new data or demos seamlessly. Reduced human engineering. No need for carefully designed prompts or workflow scripts. Strong generalization. It transfers knowledge across app features and UI patterns more easily. Continuous self-improvement. Deployed agents keep refining their skills over time. Examples like Claude Computer-Use, OS Atlas, and Octopus v2-4 illustrate how these large vision language models can be tailored for GUI tasks, representing a big leap from older designs. Now let's talk about active and lifelong agents, the next frontier in GUI automation. Even native agents depend on humans for guidance. Somebody still has to define the tasks or fix mistakes. By contrast, active lifelong agents strive for full autonomy. They set goals, check their outcomes, and learn from their own successes and failures. They don't rely on manual annotations or external interventions to keep getting better. Together. Think of the difference as how much they drive their own learning. Native agents wait for us to tell them what's missing, but lifelong agents find those gaps themselves and figure out solutions over time. It's similar to how robots learn, continuously refining actions through real-world trial and error. Look at Figure 3 here. You'll see the 4 components that power any GUI agent. Perception. Processing screenshots or textual info. Reasoning. Quick intuitive moves. System 1. Versus deliberate decision-making, System 2. Memory. both short-term for immediate context and long-term for past experiences. Action space. Clicking, typing, and other input methods, judged for how well they line up with the intended targets. These pillars set the stage for advanced agents like UITARS. Moving on to how agents perceive GUIs. It's more than just reading static images. Interfaces can change quickly. Things load, pop-ups appear, or states become disabled. Older approaches use textual structures like HTML or the Document Object Model, DOM. But that often introduced clutter. Systems like WebYC attempted to clean up the text-based input, but it was still limiting. Instead, visual screenshots are now front and center. Modern vision models let agents pinpoint specific elements with bounding boxes or labels. Tools like optical character recognition, OCR, and detection networks, e.g., IconNet, Dino, help identify text and icons on the screen. Some methods, like CACT, connect these visual elements to text descriptions for better comprehension. A big step forward is comprehensive interface modeling, which merges textual, visual, and semantic information. Something like uGround can map GUI components across different platforms, while OSCAR adds labeled metadata for deeper understanding. And because many interfaces are dynamic, agents have to watch out for changes like loaders or placeholders. Keeping actions grounded to the original screenshot and staying aware of updates helps maintain accuracy. Next is a closer look at the actions and reasoning behind GUI agents. They typically deal with a unified action space. This means defining a consistent set of actions, clicks, drags, scrolls, typing, and then mapping them to each platform in a way that makes sense. For example, a click on Windows might translate to a tap on an Android device. Some agents even incorporate language-based actions like API calls or command line inputs to handle advanced workflows. When it comes to reasoning, we often discuss System 1 versus System 2, a nod to fast versus deliberate thinking. System 1 handles quick reactions, like recognizing a familiar button or a routine action, but it's not so great for complicated tasks. That's where System 2 comes in, focusing on planning, logic, and consistency over multiple steps. Combining both allows agents to respond instantly when they should, and carefully plan when the task demands it. Let's stay on reasoning for a moment. System 2 is crucial for those big, multi-step tasks, like filling out a complicated form or diagnosing an error. Agents use milestone recognition to keep tabs on their progress. They also lean on trial and error reasoning, forming hypotheses, testing them, and adjusting based on what happens. Reflection training helps them learn from each attempt, reducing mistakes over time. Memory systems also matter a lot. In the short term, the agent tracks its immediate history, like which elements it clicked. Tools like COAT can extract interface details to maintain situational awareness. Long-term memory stores knowledge from past interactions, such as user preferences. Systems like Oxygen, Monosulfide Copilot, and Cradle use this info to refine their performance on repeated or related tasks. Finally, capability evaluation is introduced. The paper divides this into perception, understanding the interface, grounding, locating elements precisely, and broader agent capabilities. Can it actually complete tasks? Tests can be offline in controlled settings or online in dynamic ones, ensuring the agent is both accurate and robust. Now let's zero in on evaluation metrics for GUI agents. They're grouped into 3 categories: perception, grounding, and overall agent capability. Perception tests how well the agent sees and interprets the UI. Datasets like Visual Web Bench check web comprehension, and Screen QA focuses on mobile screen understanding. Another dataset, GUI World, measures multiple choice and free-form question answering, with metrics such as accuracy or Rouge L. Grounding looks at how precisely the agent pinpoints on-screen elements. Benchmarks like ScreenSpot verify single-step element targeting by comparing predicted clicks to actual bounding boxes. Agent capability split into offline and online tests. Offline tasks, like Mind2Web or Android Control, simulate static scenarios to see if the agent can pick the right actions. Online tasks, like Android World or Office Bench, place the agent in real-time interactive environments, seeing if it reaches the correct outcome. At the end, the paper introduces UITARS as a native GUI agent that avoids the usual modular pitfalls. It adapts iteratively by learning from direct feedback rather than being scripted. Here's an overview of the UITARS architecture itself. The basic loop goes like this. The agent receives an initial goal, like open this app and log in, then gets observations, screenshots, logs of what's happening, and picks an action, maybe a click or key press. it uses all the contexts, including past actions and screenshots. It keeps repeating this perceive-act cycle until the task is done. Before executing an action, UITARS generates thoughts, a hidden reflection step that helps it evaluate what just happened and what it should do next. Think of it like a mental rehearsal. Did the last action succeed or fail? What should I do next? This extra layer helps it deal with uncertainty or tricky situations. Look at figure 4 here. On one side, you'll see the environment, real-time feedback from PyAuto GUI or other tools. On the other, you'll see the agent's core capability, which includes perception, reasoning, action, and learning components. Together, they make a loop that keeps refining itself as tasks get more complicated. GUI perception is no walk in the park. It's not just about identifying objects in a scene. GUIs can be crammed with tiny 10 by 10 pixel icons that are crucial to functionality. UITARS tackles this by processing raw screenshots end to end. This is different from using separate modules for detection or classification. The advantage? It scales more effectively while managing data scarcity. To develop this capability, the researchers gathered massive sets of screenshots alongside metadata about element types and bounding boxes. Some data was automatically collected, other parts required human help. Check out figure 5 here. It illustrates various tasks the agent faces, from answering questions about specific interface elements to describing transitions when something changes on the screen. A big part of this design is memory management. UITARS uses short-term memory to keep track of the latest context, like the last few screenshots, so it doesn't waste effort on older details. That keeps it efficient, while still giving it the context it needs to act accurately. Here the focus is on how UITARS really reads and understands the screen. It labels each interface element, not just calling it a button, but noting style, location, and role. For dense captioning, UITARS gives a thorough description of the interface, which elements are where, how they fit together, and which ones might be important. It then moves on to state transition captioning, which logs what changes whenever something is clicked or hovered over. So if a user opens a dropdown, or if the system updates a label, UITARS understands that shift in context. It also supports question answering, where you can ask about the layout or the function of a specific element. Another neat trick is set of mark, which highlights elements so the model can link descriptions to actual spots on the screen. Finally, there's the concept of unified action modeling. Instead of random button presses, UITARS looks at how people typically sequence actions, like clicking settings before advanced options, and tries to follow that same logical flow. And it keeps this consistent across platforms, whether it's mobile or a desktop environment. Moving along, UITARS takes that same idea further with its unified action space, a standardized set of actions that apply to both desktop and mobile. So a desktop mouse click corresponds to a tap on mobile, making the system's behavior consistent. The data collection that feeds into this includes two main sources. First is a carefully annotated dataset, where people record every click or key press in detail. Second is open source data, providing a broader range of tasks. Accurate grounding is super important here. When you say click the red submit button, the agent has to figure out exactly where on the screen that is. Metadata and screenshots help it figure out the coordinates. Finally, the page reintroduces System 2 reasoning, deep, step-by-step thinking, that helps the agent tackle fuzzy or uncertain tasks. This extra layer of deliberation gives it the flexibility to handle unexpected states or complex user goals. Now let's talk about how UITARS learns from real-world tutorials. Datasets like Mint and Omnicorpus contain examples of people walking through GUI tasks, but there's a lot of noise. So UITARS employs a multi-step filtering system, coarse filtering. A simple classifier weeds out irrelevant text. Fine-tuned filtering. A language model refines the dataset further. Deduplication. Repeated data is removed to keep only the best tutorials. Then, reasoning augmentation comes into play. The system doesn't just observe the data. It generates thoughts between each observation and action. This is a structured way of forcing the model to think, why am I clicking here? Or, what step is next? Techniques like ActMy structure the agent's approach to consistency, milestone identification, and trial and error. This is how we move from purely reactive agents to ones that genuinely think through GUI tasks. UITARS uses several advanced reasoning patterns. Trial and error is one of them. Imagine changing Chrome's language to Japanese. If UITARS picks the wrong setting at first, it takes note of that misstep and adjusts. Another pattern is reflection, where the agent recognizes a mistake, say, choosing the wrong icon, and fixes its plan. For really big tasks, task decomposition splits a complex job into smaller steps. So if you're formatting a document, the system breaks it down into change line spacing or remove background color. Long-term consistency ensures that across all these steps, the agent doesn't lose track of the bigger goal. Milestone recognition is another part of the puzzle, helping the system mark progress, like finishing a wallpaper switch before moving on to screen resolution. Under the hood, there's a bootstrapping approach that samples thought-action pairs. The model looks at possible actions and picks those most aligned with a logical thought process. This combination of reasoning patterns gives UITARS the capacity to handle ambiguous tasks and keep improving accuracy. What about scaling up and learning from the real world? UITARS addresses this by long-term memory. Many real-world tasks aren't neatly labeled, so the agent must learn as it goes. It starts with online trace bootstrapping. The system tries tasks in virtual GUI environments and records all actions, states, and outcomes. These raw data traces then go through multiple filters. Rule-based rewards. Filter out actions that don't lead anywhere. Vision language model. Score the remaining actions based on quality. Quote. Human review. Check for any weird outliers or mistakes. After this rigorous process, the system transforms these traces into updated instructions, basically teaching itself from each cycle. Figure 7 here shows the flow from raw trace to refined instruction, showing how each pass makes UITARS more competent. Errors happen, and UITARS has a way to handle them. Reflection tuning. Whenever the agent clicks the wrong spot or tries an invalid action, a human annotator flags the error and provides the correct action. This pairing of incorrect and corrected actions creates a training signal about what not to do next time. Then there's direct preference optimization, DPO, as allows. It doesn't just look at successful actions, but also uses the incorrect ones to learn a preference for what leads to better outcomes. By comparing the agent's original action to the corrected version, the model becomes better at telling right from wrong. This method is crucial when environments change or tasks get complicated, since it helps the agent bounce back from mistakes more effectively. Training UITARS involves multiple phases. First, there's continual pre-training on a large dataset to form a solid baseline across perception, grounding, and basic interactions. Then comes an annealing phase, where you gradually feed in more complex, high-quality tasks. This helps the model adapt to real-world demands without getting overwhelmed all at once. Finally, there's the DPO phase. This is where the model learns to handle errors more gracefully. It looks at corrected actions and sees why they're better, training a preference system that rewards the good stuff and penalizes the bad. All of this sets the stage for the next part of the paper. Experimental results. UITARS is built using a QN2VL backbone and tested on various tasks to measure perception, grounding, and reasoning. Baselines include well-known models like GPT-4 and oxygen monosulfide atlas. The upcoming results highlight how System 1 and System 2 reasoning, combined with scaled-up parameter counts, affect real performance on these benchmarks. Let's examine the performance results. First up, the perception tests. UITARS 72B excels at tasks like understanding web structures, web SRC, and mobile screens, screen QA short. In Table 3, you'll see it outscore GPT-4 by a notable margin. It's really good at mapping semantic content to GUI elements. On the grounding side, Table 4 focuses on ScreenSpot Pro and ScreenSpot-V2. These require high-resolution GUI analysis across desktop, web, and mobile. UITARS 72B clocks in at 38.1 on ScreenSpot Pro, and as the model grows from 2B to 72B parameters, performance leaps up significantly. This shows just how crucial model size can be for correctly pinpointing elements in complex GUIs. Overall, these results show that UITARS' perceptual and grounding abilities are top tier, laying the groundwork for more sophisticated tasks. Now let's dive deeper into ScreenSpot benchmarks. In Table 5, various methods are compared on the original ScreenSpot test, which looks at tasks like grounding text labels or icon widgets. UITARS 72B outperforms other models in both categories, showing off its strong understanding of interface elements. Next, Table 6 addresses ScreenSpot-V2, which adds more complex scenarios, particularly on desktop apps. Again, UITARS 72B leads, with an impressive average score of 91.6. These consistent results across multiple platforms confirm that UITARS isn't just good on one type of interface. Then we shift to offline agent capability evaluations, like multimodal Mind 2 web and Android control. These are static tasks where you can see if the agent chooses the correct actions step by step. This is a great segue into how UITARS fares in both static and dynamic tests, highlighting its ability to adapt across different contexts. Taking a look at Table 7 for the Multimodal Mind 2 web benchmark, you'll see UITARS 72B leading in element accuracy, Operation F1, and success rates. That means it can handle a wide range of website tasks reliably, outperforming rivals like GPT-4o and Aguvius 72B. Check out Table 8 next. It shows results for mobile tasks and the GUI Odyssey benchmark. Here, UITARS 72B also takes the top spot for grounding, type prediction, and success rates, surpassing Oxygen, Monosulfide Atlas with a healthy margin. These offline evaluations confirm that UITARS isn't just a one-trick pony. It handles many kinds of tasks, from simple navigation to multi-step procedures. Ready to see how UITARS does in a live environment? Table 9 compares different models in OS World and Android World, which are fully interactive setups. In OS World, UITARS 72B DPO not only matches Claude's performance, but does so with fewer steps. Claude had a 50-step allowance, whereas UITARS got just 15. That's efficient. In Android World, UITARS 72B DPO stands out again. Training on varied data, including negative examples, really helps it figure out which actions are optimal. We also see the impact of scale. Comparing 7B and 72B versions of UITARS reveals big improvements in reasoning and execution. Adding System 2 reasoning on top of that just amplifies the effect, enabling more logical, step-by-step decisions. Finally, let's consider the role of reasoning in detail. Look at Figure 8 here. It shows a showdown between System-1, fast, intuitive, and SYSTEM2, deliberate, reflective, reasoning in both in-domain and out-of-domain tasks. When there's just a single correct output, like Bo1, System 2 can sometimes overthink or add irrelevant steps. That leads to mistakes like hallucinations. But as tasks offer more possible outcomes, like Bo16 or Bo64, SYSTEM2's thorough reflection pays off, boosting accuracy significantly. When we switch to out-of-domain tasks, such as those in Android World, System 2 reasoning really shines. It handles unfamiliar challenges better because it can slow down, think deeply, and adjust to new conditions. The takeaway? A hybrid approach might be best. Fine-tune System 2 for the complex, multi-step tasks without slowing it down too much for the simpler ones. And that wraps up our deep dive. Next time you're stuck booking flights or formatting docs, just imagine. Someday soon, your AI assistant might not just follow instructions. It'll debate them. Are you sure you want economy class? Thanks, UITARS.